Welcome to Global Virtual School students. This is your first year chemistry class. I am Dr. Jalbano. The topic for today's discussion from chapter 3 first year chemistry is bond length and dipole moment. Students, previously you learned about the bond energy, and also there few of their observe the bond relation between bond energy and bond length. And after this dipole moment will be discussed in today's lecture. So after completing this topic, you will be able to describe how knowledge of molecular polarity can be used to explain some of the physical and chemical properties of the molecule. We will observe this with the help of solving example, and you will be also able to describe the change in bond lengths of hetero-nuclear molecules, and that is due to difference of electronegativity values of bonded atoms. And now students, what is the bond length? As its name shows, length of the bond length. So of course this will be the length of the bond between two covalently bonded atoms. Bond length may be defined as the distance between the nuclei of atoms joined by covalent bond. And I have this example. Consider this is these are two atoms, one is this one and one is this one. They have the charge center like proton, and they have the electrons. When they come close to each other, there are two types of forces: force of attractions between positive nuclei and negative electrons, and force of repulsion between two nuclei of the two atoms and between two electrons of the two atoms. So when the force of attraction dominates the force of repulsion, and then a maximum overlaps occurs, at that stage a bond is formed. And at the distance between the center of these two nuclei, that is called the bond length. So as atoms are in continuous state of vibration motion, so we sometimes call this this is the average or minimum average of minimum internuclear distance, and that considered as a bond length or bond distance. And we can also say that internuclear distance when the maximum possible overlapping of concerned atomic orbitals occur, then that is called bond length or bond distance. And bond lengths usually these are measured by some techniques. If you are asked the question how the bond length is measured, so you have to mention the techniques like X-ray diffraction, neutron diffraction, and microwave spectroscopy. So these three techniques are used to determine the bond length of the molecules, of the bonds. And now what is this covalent radii? Students, radii is the plural of radius, and you know what is the radius? Radius is the distance from the center to the edge of a circular if you have some circular object, then that is the radius. In case of atom, the distance from the nucleus to the outer shell, that is called the radius. So covalent radii mean when two atoms are joined through a covalent bond, and the half of the distance of the bond length, that will be the covalent radii. So one half of the bond length or bond distance between nuclei of two similar atoms joined by a covalent bond is called the covalent radius of that atom. Consider this is hydrogen atom and this is also hydrogen atom. They come close to each other. There are force of attraction and repulsion, but when the force of attraction dominates, a bond is formed, and this between this nuclei, this complete length is called the bond length, and half of this, like this one, this will be covalent radius of hydrogen. So we have some values about covalent radii of some other atoms, like carbon has 0.77, and its units of distance are usually, you know, this is the meter, but this distance is very small, so the units used for bond lengths are angstrom, and 1 angstrom, you know, it is equals to 10 raised power minus 10 meter. So these are measured in angstrom. Carbon has 0.77 angstrom, nitrogen has 0.75, similarly oxygen 0.74, And you know fluorine is smaller in size than chlorine, chlorine is smaller in size than bromine, bromine is fluorine is smaller in size than chlorine, chlorine is smaller than bromine, bromine is smaller than iodine, of course. So as their size increases, their covalent radii also increases. So now come to the point that bond lengths of some covalent bonds. The covalent bonds between different atoms. This is like similar atom, but these are between different atoms. So their bond lengths are given that are in angstrom. Sometimes these bond lengths, like this is carbon chlorine bond, this bond length is 1.76 and it should be equal to the bond length covalent radius of carbon and covalent radius of chlorine. Now we have this carbon bond is 0.77 and chlorine radius is 0.99, and when you add this is exact equal to 1.76, but not in all the case. Sometimes their bond lengths varies. How they vary? For example, we take the example of this Cn. This should be equal to covalent radius of carbon, that is 0.77, and covalent radius of nitrogen, that is 0.75. So it should be equal to, its sum should be equal to 1.5747, but in actual this is equal to 1.52 angstrom. So these are not exact equal by just adding the covalent radii of the two atoms and their bond lengths. Similarly, you can observe in CO, its bond length should be equal to radius of carbon 0.77 and radius of oxygen here in this case 0.74, and it should be equal to 1.42, but in actual this comes 1.51 angstrom. So these are not exact equal. So it means there is some influence of the electronegativity of the atom that influence the bond length of the covalent bonds. So this shrinkage in bond length becomes even more and more marked, even more and more observable as the difference in electronegativity of the two bonded atoms increases. And you know, like this fluorine, it has carbon fluorine has greater electronegative difference than bromine, so their difference of electronegativity due to their bond lengths also varies. And now what is the effect of hybridization on the bond length? In this we have learned hybridization of three types: sp, sp2 and sp3. In sp3, s character is like 25% its contribution and p's contribution is 75%, and in sp2 1s and 2p, so this contribution is 33% and 67%. In 1s and 1p, so there is 50% contribution of S and 50% contribution of P. So as the contribution of S character increases, their bond length decreases. Like if for carbon if it is sp3 hybridized, CH bond it is 1.11, but if it is sp2 hybridization it is 1.10. If it is sp it is 1.08. This bond length reduces, and bond length reduces, bond is stronger and bond energy will be higher. In this case, in ethanol, carbon, if it is sp3 hybridized, then CO bond length is 1.41. If carbon is sp2 hybridized, then bond length in formic acid CO is 1.34. Similarly for Cn, as the S character increases, bond length decreases. Bond length decrease means bond strength increases. Bond strength means bond energy, higher bond energy. So in previously you also observed that as the sp2, sp they increases, their bond length decreases but their bond energy increases. So this is due to increase in S character. And hybrid orbital with increased S character is held more tightly by the nucleus. So there is more force of attraction. So more of the energy required to break, and lesser will be the distance, bond length will be reduced. So what about a single, double and triple bond? Like this is between carbon, carbon single bond, this between carbon double bond, this between is carbon triple bond. And you can observe clearly single bond has greater bond length, double bond is lesser than single bond, and triple bond is even lesser than double and single bond. And this is why this happens, because due to presence of pi electrons in case of double bond and also more pi electron in case of triple bond, and there is more force of attraction and bond length reduces, and again bond length reduces, bond energy increases. In case of Cn, when Cn has a single bond, its bond length is higher. When Cn has double bond, its bond length reduces. When it is triple bond, its bond length further reduces. And same for the carbon oxygen single and double bond. So double bond between two atoms is shorter than a single bond, and triple bond is shorter than a double bond. And this shrinkage of multi-bond is due to presence of, I already told you, the presence of this pi bond. Pi bond means 2 pi electron. In this case, 2 pi bond means 4 pi electron. So pi electron, they exert additional attraction and bringing the nuclei closer to each other. So their bond length reduces. So what is the dipole moment? This is represented by mu and by this symbol. This is like written in mu, and this is the product of its multiplication, or this is the product of magnitude of the charge and the distance between them. And dipole moment also has the magnitude and it is directional quantity. So a charge represented by Q and distance represented by R. So its dipole moment will be equal to charge into distance, and of course units will be, for charge it is coulombs and R for meter. So it's just units is coulombs, SI unit is coulombs meter, but there is that commonly used unit is dBi from the scientist name. 1 dBi is larger unit, while coulomb meter is smaller unit, and 1 dBi is equal to 3.336 10 raised power minus 30 coulombs meter. So dipole moment is a magnitude of charge and distance, and its unit is coulomb meter, but SI unit, but generally the unit used is dBi. dBi is largest unit and coulomb meter is a smaller unit. And what is its application? What is its use of dipole moment? First, it determines the polarity of the molecules. So usually non-polar molecules, they have zero dipole moment. For example, benzene. While polar molecules, they have some value of the dipole moment, like chlorobenzene, it is 1.2 dBi. So you have to memorize their dipole moment values. Its application is, we can predict the isomers. Isomers, students, this is actually the stereochemistry, and this is the arrangement of the atom in space. So for example, we have 1,2-dichloroethene. First of all, what is ethene? You know, ethene, this is the ethene, H. But if one of hydrogen from this carbon and one of hydrogen from this carbon, they are replaced by chlorine, then this is called dichloroethene. So dichloroethene, this chlorine can be arranged in two ways. One chlorine in this direction, one chlorine in this direction. But there is possibility these two chlorines are on one side and two hydrogen are on another side, because this is the spatial arrangement. And I already told you that dipole moment has direction and magnitude. Like this is from positive to negative. This is represented by this arrow and with this cross. And in this case, by this arrow and cross, this is positive and this is negative. This points from positive towards the negative. And in physics, you know, this is a vector quantity. When two vectors are in opposite direction and of the same magnitude, they cancel the effect of each other and they have zero value. So in a transform, this is a trans. When two functional groups are on opposite direction, then this is called the transform. So this is trans 1,2-dichloroethene. So, and it has zero dipole moment. But when those chlorines are on the same side, this is called the cis form. and in this case the dipole moment has value because now dipole moments are in same direction and they have the magnitude and they are added, so it has dipole moment 1.89 d by. It means the values shows this is cis and the zero value shows this is the transform of the molecule. The most important application is we can calculate the percentage ionic character in a bond, how much this bond is ionic and how much this is covalent. This will be explained with the help of example. Let's focus on this example. Calculate percentage ionic character in a bond. Example is observe dipole moment of HF. HF dipole moment is 1.90 d by. Find the percentage ionic character in HF. Distance is given and charge is also given. So just apply the dipole moment formula that is Q into R, and now we suppose HF is a completely 100% ionic. Fluorine has a fully negative charge and hydrogen has fully positive charge, and the formula is charge into R. Charge is given, distance is also given, so multiply this and you can find the calculated dipole moment, that is 1.469 10 raised by minus 29 coulombs meter, and we know 1 d by is equal to 3.336 10 raised by minus 30 coulombs meter. And now we divide this by this value and we observe this in the form of d by. So this is calculated or ionic, you can say, the dipole moment, and the observed dipole moment from some techniques, that is 1.90. So dividing the observed by calculated and multiplying with 100, you can find the percentage ionic character, that is 43.2%. So HF, it is 43.2% ionic, and it means it is 57% covalent. So due to this ionic character, this is even more stable. In HCl, this ionic character is little lesser, but it has ionic character. In HBr, it has even smaller ionic character. So dipole moment can be used to calculate the ionic character of the bonds. So now question is, carbon can make a bond with hydrogen to form ethyne, and you know this is the ethyne. This question can be asked from the sp hybridization, and also here like bond energy of CH is same, this is same in this case and in this case CH. For ethyne, either 2s and 2p, you know, and this carbon 2s and 2p are involved, which are difference in energy, but actually these not pure 2s and 2p, they were hybrid to form sp hybrid orbitals. Explain the formation of ethyne, so you have to explain like this sp on one carbon and sp on one carbon is this one with one electron, and similarly second carbon, this also has sp with one carbon each. So first bond formed between sp and they form bond with s of hydrogen and s of hydrogen. These bonds are same, hydrogen and hydrogen, but here this case one is sigma, and the 2py and 2pz are on and they are parallel to each other, this line. So they parallelly form pi bonds this way. So there are two pi bonds that are due to parallel, but these bond energies are the same because they are formed by sps and also in this side sps. So you have to explain the what type of hybridization sp. You have to tell about the bonds, how many sigma and pi bonds, and its shape, you know, it's linear and its angle is 180. So these questions can be asked in the part of bond energy as well as in the hybridization topic. So this was all about the bond length and relation with the bond energy and dipole moment, its application. Our next topic will be the effect of bonding on properties of the compounds, properties like physical or chemical properties.